All right, we're going to take a look at 4-5 day 1. We are still in chapter 4, believe it or not, and we are trying to solve using square roots, except for my dogs are like super not cooperating. So they're going to bark and growl and be really super annoying during this video, but I don't really have a choice. So here we go. We aren't really going to do any solving today. Today we're going to learn some skills about how to simplify radicals and do like adding or multiplying, because those skills will pop up when we do start solving in day 2. So there's kind of a series of ways to do this. First of all, you need to know what your perfect squares are. So like 4 is going to be 2 squared, 9, 3 squared, 4 squared is going to give you 16, 5 squared, and so on. So let's know these. And I'm on 7 times 7, 8 times 8, 9 times 9, and 10 times 10. That's probably good enough for now. Okay, so I would also get out that blue card, your factor card. That'll come out in really handy in what we're doing today. So the first thing we're going to do is just simplify. So you aren't going to be able to write your answers as fractions or decimals, so you're going to need to simplify the radical, which means you look for the biggest perfect square that goes evenly into the number. That is where your blue card is going to come in pretty handy. And then let's just do some. So here's 20. So if you take out your blue card, you're looking for a number pair that contains one of these perfect squares from up above. So if you look at your number card, for example, for 20, you're going to see 1 times 20, 2 times 10, and 4 times 5. So you're looking for the biggest perfect square. Well, that's 4. It's actually the only number that's on my perfect squares list. That's what this is. These are my perfect squares. So I'm going to split this into root 4 times root 5. And a root, like square root, is kind of like a little math prison. You can get out if you're a perfect square. If you're not, too bad. You're stuck in there. So the square root of 4 is going to come out as a 2, and then the root 5 is going to be left inside, and that is the simplified version of that. So when it says no decimals, simplify your radicals, that's what you're going to have. So now look at your blue card and look at 27. If you look and you're looking for the biggest perfect square, you see a 9 times 3 option. And the reason you pick 9 is it's on your perfect squares list from up above. It comes out as a regular 3. The other 3 is stuck in, and that is simplified. Now in 48, you're going to see on your blue card a couple different options. You have 1 and 48, you're going to have 2 and 24, you're going to have 3, 8, 4, 6, and that's probably it. So, no, that's not it, because it's not 3 times 8. I was doing 24, sorry. It's going to be 3 times 16. I started doing 24 instead of 48 for some reason. So as you go through here, you're going to have 4 times 12. That's it. Oh, 6 times 8. So what you're looking for are those numbers from the perfect squares list. So 4 is on it, but so is 16, and you always want to pick the biggest one. It says right here, biggest perfect square. So I'm going to pick 16 and 3. Because then the 16 comes out as a 4, the 3 is stuck in, and I'm done. If I had picked the 4 and the 12, I would have to do another layer, because let's just pretend I had done that. If I had picked 4 and 12 to split this into, this would have come out as a 2, but this could still be broken down again into another perfect square, and it would just get really confusing. But in the end, I get the same answer. So just find that biggest perfect square, and then you can avoid all of that confusion. If I look at my blue card for 32, I find that 16 and 2 is going to be my biggest perfect square. 16 comes out as a 4, 2 is the leftovers that kind of gets stuck underneath. So that's going to be when you see it just saying simplify, and it'll say that on the whole thing, simplify your answers. Now we're going to multiply. Basically, numbers that are on the outside can multiply together, and numbers that are underneath the radical can multiply together. So in this first problem, and then you have to simplify like we just learned. There isn't any number outside, so the 2 numbers underneath the radical go ahead and multiply. But then you have to go and do what we did up above, find any perfect squares that are in there and get them out. So that's the only fully correct answer to that problem. Here, I do have some numbers on the outside, and then I have two numbers that would multiply underneath. And if you look on your blue card, 15 doesn't actually divide into anything from your perfect squares list, so you're done. Here, there's only a 6 on the outside. This one like has a 1. So the 6 and the 1 are going to put a 6 on the outside. And when you take 5 times 15, you're going to have 75. Look on your blue card and you're going to find that it splits into 25 times 3. This is a 5, and then now that the 5 is on the outside with the 6, they multiply together, and your final answer looks like that. So this one's more advanced, same kind of process, but now you're going to need to distribute or FOIL. Those are skills you already have. We're adding to that simplify the radicals, which is our new skill from today, and combining like terms, which you already know. So there's a lot of steps, but we actually know how to do all of them from before. So if I multiply this, I'm distributing that. Only the 3 is on the outside. The 2 and the 6 are on the inside, so they make a 12. Here, I'm going to be multiplying those, and since that's negative, it stays negative. The 3 and the 5 multiply because they're both regular numbers, and the radical number 2 doesn't multiply by anything because there's not another radical with the 5. However, now I have to simplify, meaning look at those numbers under the radical and decide if they can break down into perfect squares. 12 we've done a few times, and that can break down further. The square root of 4 is a 2. So now all together I have a 6 root 3 because these two multiplied together once they're both on the outside. This I can't do anything with because the root 2 doesn't break down. And these I can't add because you can only add them if the radical part is the same. So it's kind of like having 6x minus 15y. They just don't go together. This one is set up to FOIL, and if you're like, I don't know how to FOIL, it's like high time to learn because we've been doing it forever, and now it's just taking on another layer of having the radicals in it. So the first times the first will be 14. Here, the 7 and the 3 multiply together, but there's not another radical to mix with the 2. Here, the 2 is on the outside, the 8 is on the inside, so they don't actually multiply. And then here, think this one through, you have a negative 3 on the outside, and then the 8 times 2, since they're both inside, becomes 16. But now that we did the foiling, we have to go through and look for any opportunity to simplify. So I can see that I have my 14. This one does not simplify because 2 is under the radical and it only breaks into 1 and 2, so there's no squares in it. 8 and 16 are a different story though. Here's my 2. This can break into 4 times 2. This would come out as a 2 because that's the square root of 4. So I end up with a 2 times 2 or a 4 on the outside and then that root 2 from over here. And then this one's also kind of weird because I have a negative 3, and then the square root of 16 is just a straight up 4, no leftovers. So that product becomes a minus 12 at the end. So I had to FOIL, then I have to simplify. I'm just following the steps that are listed on the notes, and then last I have to combine if I can. Well, I can because I have a 14 in the front, which is just a number, and a minus 12 at the end. So just like elementary school, 14 minus 12 is 2. And then these two actually do go together because they are both square roots of 2. So if you have negative 21 of something and you add 4 of the same thing, you wind up with negative 17 of those. So you're just saying, well, they're alike and I can add them together. Okay, so now division isn't really division so much. You kind of separate and conquer them. So you're going to split them up and then simplify anything you can, like in terms of the radicals. So again, the second step is the only new thing. And what this simplify means is you reduce if you can. And I'll show you as we go. So in this problem, you can't do anything with the square root of 2, but the square root of 25 is 5. I can't reduce or do anything with that, so that just is my final answer. Here, I'm going to split them up like it says and then look at each piece separately. This can split into 4 times 3, so that will be a 2 on the outside from the square root of 4, and the 3 is caught inside. And this is just the square root, square root of 49 is just a plain old 7. So what it means by simplify or reduce is that you look at these outside numbers when you're done, and if they reduce, you reduce them, but 2/7 doesn't, so you're done. All right, so the really hairy, messy, icky ones are right here. We are going to do what's called a conjugate. So basically, you have to get rid of the square root on the bottom. So write yourself a little note. You can have no square roots on the bottom. And the term that you might have heard in Algebra 1 is to rationalize. So you're trying to rationalize the bottom, which is fancy name denominator. So if you rationalize the denominator, you're getting rid of that square root on the bottom. And the way to do that is to multiply something like by itself. Because if I have the square root of 3 and I multiply it by another square root of 3, it becomes the square root of 9, which becomes a regular 3. That works for every number. So if you have the square root of a number and you multiply it by the square root of that same number, it just turns out to be that number without a square. So if you just kind of learn that pattern, it makes your life a lot easier. So here I'm going to split this up like we did before. The 16 becomes a regular 4, but I'm stuck with the square root of 3. Up here I had the radicals on the top, and that's fine. I just can't have them on the bottom. So now I'm going to do that rationalizing, and to get rid of a root 3, I use a root 3. Whatever you do to the bottom, you do to the top so that everything stays in balance. On the top, the 4 and the 3 don't intermingle because one's on the outside and one's on the inside. But the bottom, using what we just talked about up in the top left corner here, lands me at 3. And then I just take a quick look at the numbers that are on the outside, the 4 and the 3, to see if they reduce, and they don't. So this is my final answer. So here, this one's kind of weird, but to get rid of the root 7, I just use another root 7. Whatever I do to the bottom, I do to the top. So the top, from what we learned above, the 2 is the only thing on the outside, but the 3 and 7 are together inside, so they'll become a 21. And then on the bottom, root 7 times root 7 will just turn out to be a 7 because it would actually be a root 49, but the square root of 49 is 7. And if you look on your blue card, you're going to find that 21 does not contain any perfect squares, so there's nothing you can do with that. And the 2 over 7 on the outside doesn't reduce. So actually your final answer looks like this. It's kind of a messy answer, but it's kind of a messy problem. And in the end, I don't have a denominator bottom with radical, so I'm good to go. The top can be as gross as it needs to be, but the bottom just cannot have square roots. So here we're going to use a little trick. We're going to use what's called the conjugate of this. Conjugate is like the thing that will clear that out. And what we do is we end up, and it says this right up here in your notes, if the denominator is a plus root b, multiply by a minus, and vice versa. So whatever this is for plus root 5i, I'm going to use a minus. And even though that's messy, I have to multiply the top by that as well to keep it balanced. And then I mathed the top and the bottom separately. I'm going to go ahead and do the top right now. And that's going to be like what we learned up above. So these are just kind of layering as we go to each new section. 3 times 4 is 12. And then here, the 3 doesn't actually multiply with the 5 because the 5's on the inside and the 3's on the outside. So that's what I get on top. It's icky, but nobody cares. And you can't do 12 minus 3 and get 9 because the 12 doesn't have a radical. So it'd be like having 12 minus 3x. You can't put them together. Now, the bottom I need to FOIL. And the reason I'm using this opposite sign is that these two, every single time, if you do this properly, should cancel out. And then I won't end up with any radicals. I'll show you. Here I'm going to take my first two, 4 times 4. Then the outside is going to be a minus 4 root 5. The inside is a positive 4 root 5 because the 4 and the 5 don't multiply since one on a regular number and one's inside the root. And then this last part, can you see that you're going to have a positive times a negative, so negative, and you're going to have root 5 times root 5, which is going to turn into a regular 5. Because technically it's the square root of 25. So what always happens if you use that opposite sign conjugate is these will cancel, and the last thing becomes a number. So I have 16 minus 5, so the bottom is just going to be an 11. And then I take a look at that. And the only way you could ever reduce this is if some number went into 12 and 11 and also into 3, but nothing divides out of there. So I can't reduce it, and that is my final answer. It is also okay, and depending on who you have for a teacher, they might split it up and write it as 12 over 11 and then minus 3 root 5 over 11. But it doesn't really matter. They're mathematically the same thing. So those do get a little messy. This last one is going to be like the king of messiness because I'm going to end up having to FOIL the top and the bottom. So in order to get rid of a 2 plus root 3, I'm going to go ahead and use that conjugate 2 plus. So I had a minus, now I used a plus. Whatever I whatever I multiply the bottom by, I have to do the top as well. So the unfortunate part in this problem is the top and the bottom are going to FOIL. So let's go ahead and do the top first. 1 times 2 is 2. 1 times root 3, root 3. The insides, I have a 2 and a root 5, but they don't actually multiply to be a 10 because one's on the outside and one's on the inside. And then don't let this last part confuse you. You have a root 5 times a root 3, which is going to be a root 15. So this is just like what we practiced earlier. But what's weird about this is none of those go together. And looking at the numbers inside the radicals and checking my blue sheet, none of those contain a perfect square. So my top is that 2 plus the square root of 3 plus 2 square roots of 5 plus the square root of 15. Like I said, the top can be as messy as it wants, but now the bottom has to just be a number. So let's FOIL that out. 2 times 2, 4. Here, I get a positive 2 root 3. And on the inside, I get a negative 2 root 3, as I should, because they're opposite and equal, so they'll cancel out. And then the last part is a negative times a positive, so negative. Root 3 times root 3 is root 9, so this is just a regular 3. So these cancel as they should. 4 minus 3 actually just puts a 1 on the bottom. And so I probably wouldn't even write it over 1. I would just leave that top as my answer and call it good. Sometimes you'll have a number on the bottom, but sometimes it turns into 1 and goes away. So that, my friends, is all the skills that you're going to need to use. And then tomorrow we'll get into how to use that to solve. The solving part's easy because you're already good at that. This just layer of how do I manage the square roots. So today's lesson is actually going to be a little bit heavier for you to learn than what we do tomorrow. Hope this helps. Bye.